everybody, this is BKC back in From the Depths on the engine test platform. Today's topic I want to go into something I touched on in other videos, but I just want to make sure it's very clear because it's pretty important. And that's serial or series and parallel as it pertains to the exhaust. So if we pretend that our metal block wall here would be like a typical four-cylinder engine like in a car, and then these exhaust pipes would be the manifold, okay, and then each one of these points is a cylinder. So the exhaust pipe would come out, the manifold collects the exhaust from the cylinders, and the red exhaust pipes are parallel exhaust pipes. They're collecting the exhaust. Each exhaust pipe is collecting an exhaust, and they're in parallel. If I would take off this entire straight piece right here and put them open to the air, you could stick a banana in this one and it would hurt this cylinder, but it wouldn't affect this cylinder in any way, shape, or form. Even with the straight pipe on, you stick a banana in this cylinder or clog that cylinder, and it doesn't affect these three cylinders. They could still breathe and exhaust into the pipe. So therefore they are parallel, and that's what's important, that one cylinder doesn't affect the other. That's what makes it parallel. You put a banana in this exhaust, it wouldn't affect these three. So at the point where it's painted red, that is still parallel, because it doesn't one doesn't affect the other. But right here at this T-junction, these two pipes come into become the same pipe. And in a real car, you would have double the back pressure right here, and then as you started getting more and more, you'd start getting more and more back pressure. So this cylinder would see more back pressure than that cylinder, and that's why we use on real race cars, we use balanced manifolds where they have four pipes equal length, and then they all feed into one junction point at the same time, so they all see equal so all cylinders run exactly the same. But we don't have that problem in From the Depths, so technically it would only be when two pipes become one pipe, and then this technically on a real engine would have two back pressure, and then this one would be, and then when it connects into here, this one would have three back pressure. But From the Depths, all we need to know is series and parallel. The red is parallel exhaust, where one doesn't affect the other, and then the black is where it becomes series. What we're doing is we're stacking up these pipes in a series, and then the parallel is connecting into them. So if I stuck a banana here, it would affect these three cylinders. It wouldn't affect this one, but it would still affect these three, and that's just because of the layout. If it was all going into one pipe at the same time, if you plugged up that pipe, it would affect all four at the same time, which would be equivalent to, you know, sticking a banana in here. So that is series and parallel, and that's what we need to understand in From the Depths. You don't really use it that often, but you just need to be aware of it because it comes into play when you're trying to troubleshoot a motor or making it more efficient. The only real reason we use it is when we're talking about turbocharger setup versus series and parallel, and that's kind of what I want to get into. These two motors over here, this motor has four of what you call, air quotes, non-inline turbochargers, but I've explained that there's no difference between them, and each one is collecting one exhaust. So if you think of one cylinder on a From the Depths engine as being a little four-cylinder because it has four exhaust out, and you need the fifth to either put a carb or or an injector. So, and then if you use an injector, you're not going to use turbos anyway because there's no way to connect them. but each turbo is collecting one exhaust. And if I put a banana in this one, or this turbo went dysfunctional, it wouldn't affect this turbo or this turbo or this turbo. And to be honest, if this engine would just take a hit on this turbo and this turbo would just completely disappear, it wouldn't affect the engine in any way, shape, or form, except it would just lose a little bit of efficiency because it lost a turbo. The other 3 turbos would go on just fine, and the motor wouldn't lose any power. It would just start drinking more fuel. That's the only thing that would happen to this particular motor, because turbos are in parallel with each other. And then once they join up in 2 of them join up into a serial exhaust on this side, and 2 join up onto a serial exhaust on this side. But the game doesn't care about what happens to the exhaust. The only thing it really cares about is when it's exiting the ship. If it exits the ship, it provides full cooling, and if it doesn't exit the ship, it says reduced cooling. I haven't confirmed that how much that is, or if it's even active, but in this particular case, we could damage one turbocharger without affecting the other turbochargers, and that's because it's serial. Now on this, it's just like the example over there. We have the exhaust manifold. This one's a parallel exhaust up until this T point where it joins 2 in, and then it comes around to here and collects all 4 exhausts in parallel. So if I would plug up right here, this exhaust would be affected, but none of these would be affected. And so all 4 of these exhausts here are parallel. Now when they get to this pipe, they become series, and they go through the turbos in a series. They come in through here, out through here, into this turbo, out this turbo, in through this one, out this one, into here, and then out the back of the exhaust. Now, one thing to note on turbochargers, there is no they don't care which way the turbo flows. It just be like a box fan in your house. It blows one way, but if you could reverse the motor, it would blow the other way just fine. The fan wouldn't care. It would just be a matter of rotation. Turbos and superchargers, the turbos work that way also in this game. So in real life they would be a little less efficient, but they would work. They just would be probably way less efficient. But from the depths, the game doesn't care. So we could come in on either side of a turbo, and it wouldn't really care. But where this relates to on this engine, if we take out this turbo right here, we lose all exhaust to any turbo that is downline, that is in series with it. So this engine, we could lose a turbo, it wouldn't affect anything. It'd still make 100 horsepower. It would just lose a quarter of its efficiency boost off of these turbos. And then this motor, if we lose anything, we lose from any of these pipes really, because if we lost this pipe at the top, the back pressure would come around and go out and wouldn't go into the turbos. So this motor, it puts the turbos in series, and it becomes 4 times. This one, what it's doing is, let's say each turbo gives us a 10% efficiency boost. All it is doing is saying, okay, well, here, this carburetor gets a 10 times efficiency boost. It's not adding anything up. It's it might be something like where you add one, it gives you a 10% boost, and the second one gives you 10% of that 10%. I don't really know about the formula that much, because the efficiency boost is so little in this configuration that I don't even worry about it, and you'll never really see any of my designs with this. It's more survivable, but it's not more efficient. And so if it's not more efficient, I need more gas tanks, and then it just snowballs. So I don't use it. But in here, we actually become weaker because this entire wrapped exhaust around this single cylinder, any hit on that, it's more delicate and we lose all efficiency. But what we gain by taking on that disadvantage is, say each turbo gives me 10%, this turbo gives me 10%, then it chains into this one and it gets the exact same, it would be the exact same thing as this, but what happens here is each one of these turbos is receiving one exhaust. And here each turbo is receiving 4 exhausts. So what's happening is, if you would get 10% boost with one exhaust, you're getting 4 exhausts into each turbo here, so you get 4 times more efficient. You would get 4 times more efficiency in this engine, and it shows up in the efficiency ratings here. We see this motor right here has 184 power per fuel, and it jumps down to 176, and then it goes down to 168, and I'll explain why that is in a minute with the power curve. And then on this motor, you could see from 184 to 229, and then we go from 176, and then we go to 361. We're becoming way more efficient. And then at 168 to 490. So you can see where collecting your exhaust parallel and then send them series into a pair of superchargers becomes way more efficient than going parallel into a parallel turbochargers. And that's what is important to note, that there is no difference between the two turbos. And some videos will say, oh, inlines are way more efficient, always use inlines, and they're not talking about the inline turbocharger. They're talking about this inline configuration of being serial. And a good example of that, and I can prove that there's no difference, is that this is a 15 cylinder inline, and it has or beam motor I call it, and it has non-inline turbos. This is the exact same motor, but it has inline turbos, and I have to do a little disassembly here to prove my point, but I got to take these turbos off because this motor is a tiny bit more efficient because of all these superchargers. But I'm going to take them off just to prove the point that there's no difference between them. Now the two motors are mechanically identical. This just has, using non-inlines, is more dense because it takes up less space. These little connection pipes take up more space. So the argument would be that inlines are more efficient. Well, in here, this motor has a lower density because of the inline. So this is an example that just bucks that right in the face and shows that these two motors are identical. So let's run them. We'll run them at 100%. We don't need to see the mid-ranges. This motor is making 1500 horsepower, 1.2 at 1288. This motor's making 1.2 fuel at 1288. They run identically. And if I did that for all the numbers, this motor kept its stats because it's exactly the same. So if I run this one at mid-range, it should be 653. If I run it at 50%, 653 exactly. And then if I run it at 10%, 247, which is what's on the card on this one, 247. So that proves that inline turbos, air quotes, inline turbos and just regular turbos run exactly the same. And a lot of videos don't make that clear. They make it sound like, oh, the inline is a more efficient, you should always use inlines, and that's just not true. The reason for that is the game doesn't see the two parts as any difference. The only difference between the two is these connect to the carburetor, and then the exhaust connects this way. And it almost to me seems like they designed it to be, this would be a parallel connection turbo system, and these were going to be a serial connection system. And but there is some designs like this that make better use of non-inlines. This motor has a lot of non-inlines. This motor has a lot of non-inlines, and then this motor, I think it's this motor right here, I've got a whole bunch of non-inlines, and then I got a few inlines mixed in with it. And the game doesn't care. The game can care less which one you use. It's just that inlines a lot of times are easier to place and more useful because of the fact that the regular turbos connect facing, the exhaust faces the cylinder, so you can only rotate it up, forward, down, and back. And then if you rotate this turbo down, the exhaust pipe would have to go this way, which this supercharger would be, this turbocharger would be in the way, and you couldn't connect it. So a lot of times if I would put non-inlines here, all the exhaust would be facing down toward the supercharger, and there's no pipe that I could use to connect them all. So sometimes, not always, inlines can be more efficient for layout purposes, but I find that the non-inlines a lot of times are more. Actually, a lot of my motors have more non-inlines. I'd say it's roughly about half and half, but there's no difference. And the reason, we'll talk about this a little bit. The reason for that is that the game uses two calculations. Okay, so if you notice, if I highlight the motor, if I highlight the engine block or the cylinder or the carburetor, you'll notice that it highlights what I call the core of the motor: the engine block, the cylinder, the carburetor, and the supercharger. And then if I highlight a turbo on any motor, it highlights the exhaust. And the reason for that is the game treats the inside of the motor, the core of the motor, as one entity. It's probably using the same formula, a tweaked formula of what the old engine system used, because we didn't have we had exhaust, but they kind of acted like a supercharger where they would just cool the motor a little bit and maybe add a little efficiency, but you couldn't chain them all together. And then when we upgraded the engine system, we had to redo the formula to affect the exhaust. So the core uses one formula, and that's why the supercharger is included in the core. All the formula is doing is looking at, is saying, how many exhausts do we have? It says, okay, we have we have one cylinder. And then it says, okay, well, how many carburetors touches that cylinder? And it says 1. So it says, okay, we're making 100 horsepower. And then it says, well, how many superchargers? And we're making 100 horsepower, and say we're using 0.1 fuel. And then it says, okay, well, how many superchargers are connected to that carburetor? And this motor says 1. So it says, okay, we're a 100 horsepower motor. We're using 1.1 fuel. We're using 1 fuel a second, and we got a one supercharger. So we're going to apply a 30% boost to efficiency at 0 RPMs, and then it's going to taper off to, say, a 3% boost at 100% RPM. And that's all that the core calculates out. That's all that it does. It doesn't care about anything else. Well, unless you have, it still wouldn't calculate out the exhaust for the parallel. But we're not really, like I said, I'm not really going to get into these because we don't. If you're going for maximum efficiency and you're watching this video, it's another thing you're not going to want to do. But this engine would say, okay, so it uses 0.1 fuel, and then so we got 30% boost, so we're going to knock that down to, I think it was 0.777 or 0.78 or something like that, which would round up to like a 0.8 fuel use per second. And that's all the core calculation does. That's all that it does. And then when you get into more complex motors, it has to say, well, how many cylinders do we have total? And that usually reports on your engine block. We got 12 cylinders in this motor. But then it says we have 24 carbs, because the carbs touch more than one cylinder. So it just reports back how many carbs that the cylinder sees, and then it goes, well, okay, well, if we have 24 carbs, we're going to be making 2,400 horsepower. If we actually had 24 carbs, they would only be touching one cylinder apiece, and since we only got 12 cylinders, we'd only have 1,200 horsepower. So this, looking at this stat at the engine block, really tells you a lot. But see, it says we have 40 turbochargers, and there's no way I don't think we have 40 turbochargers on here. I think we only got 20. But it's just telling us how many of anything, and this lets us see the core formula pretty well. It gives a good example. Like, this is 44 cylinders, but it thinks it has 64 carbs because a lot of the carbs, I think it only has, let's see, that's 8. It only has 16 carbs. So it's thinking that it's touching I think 4 cylinders per carburetor. So it's multiplying the number of carburetors. And then it says it has 128, that's 8, it's only 32 turbos, but it says it has 128 turbos. So you could see that a turbo touching a carb that touches 4 cylinders, it reports as 4 turbos. So these motors you're not going to really notice because it's got 1 cylinder, 1 carb, 1 supercharger, 4 turbos. This motor says the same thing. It reports exactly. So the formula doesn't really care whether we're series or parallel exhaust. You'll get the same results. It shows the exact same thing. But if we look at the efficiency rating, the efficiency ratings of the serial collection exhaust the parallel collection exhaust going into the serial turbos, we have gotten way more efficient. And you go, well, why is that? Why is the what they call inline turbos more efficient? And the reason for that is the exhaust has another formula. And what the formula does is it takes the output, all it cares about is the output of the core formula, that we're a 1 horsepower, 1 cylinder, we're burning 0.78 fuel. It takes those core number stats and it uses them and plugs them into another formula that goes, I think, on it. What it does is it looks at how many exhausts you have, how many exhaust is being fed into the exhaust. So that is your parallel side. How many exhaust is going into the chain? And we can see that if we run the motor. If we run the motor, we can see what the formula is using by looking at any turbo in a parallel serial parallel exhaust system. The parallel exhaust, you see it's saying that we're using 4 gases. So it's saying that this manifold, the parallel side, is collecting 4 gases and putting it into the first one. If we look at the third turbo, it's saying 4 gases. They're all receiving 4 gases. So that's what the exhaust formula is using. And if we run this motor at, like, let's go down to 10%. RPM affects that gas output. You notice at 10%, we're receiving 1/10 of an exhaust, but we got 4 of them. And see, it's showing up there. It's 0.4 exhaust gas used by this turbo. And notice the efficiency is 1.08. That's the efficiency of the motor, and then it's putting an extra 8% efficiency onto it. And then as we go to 50%, we should be getting 2 exhaust gases, and the efficiency should rise. So we are receiving 2 exhaust gases because we're receiving a half. We're receiving a half of 4 exhaust gases, and a half of 4 is 2. And then the efficiency has gone up to 31%. So if you remember that a supercharger is somewhere around the 30% mark, the turbos are now slightly more efficient. Remember, the superchargers start off at 30% efficient at no RPM, and then they start tapering down to say like 3% at 100%, which I don't know the exact numbers. I haven't really tracked it down, but it's for the way I design motors, it's not really relevant. What is relevant is that at half, when they receive 2 exhaust gases, a turbo becomes more efficient at a 50% RPM, and then a turbo went from almost no efficiency, only like a 8%, to 31% by bringing the exhaust gases way up. And then if we go to 100% load, we should be receiving the full 4 exhaust gases, and now we got a 54% efficiency increase. So that is why series and parallel is different. If we go to this motor and we run it at full percent, we look at the turbo, it just receives 18%, whereas this turbo is receiving 54% because it's receiving 4 times, and it's a slightly exponential curve. It's not a very hard exponential curve, but feeding more double in, you get more than double back. So it starts becoming more and more and more and more and more efficient. So you say, well, BKC wouldn't just putting like 100 or 200 exhaust into a series turbo system become like thousands and thousands of percent efficient? And it would be if From the Depths didn't put a hard limit on it. And we can see that in this motor over here, because if we run this motor at, it won't run at full percent because I don't have I can only have about 5,500 load. I'd have to go put the shield projector on, but it'll show us enough. This turbo thinks this is where all the exhaust is collected. It comes in right here. This turbo sees 111.3 gas. I think it tops out at 128 at a full load. So it thinks it's getting 128 exhaust gas, and we're getting a 393% efficiency. Now, you say, wow, that's way more than that little motor over there. But what we need to know is that they put a hard limit on turbos at 30 exhausts. So I don't know where 30 exhausts would be in this motor. Probably somewhere around in maybe the 20% range. Let's see. Yeah, 25. You see, as it dropped below 30, it's now 348. It's not that much less efficiency, but it is less efficient. And then if I brought it up to, let's go 25% and see if it'll go 30. Yeah, 32. It maxed out at 393%. So the exhaust gases on the motor, it becomes the most efficient at 30 exhaust gases, and then it tops out after that. And what happens in the motor, what happens in big motors like this, if I'm running this motor at 25%, it becomes maximum efficiency, and it becomes the most efficient that turbo could be. And then as you start revving RPMs, we start drinking more fuel, but the turbos can't provide any more efficiency to continue making the motor more efficient. So ideally what you would want to do is you would want to make motors all be 100% efficient at 100% load. You'd want them to be 100% turbo efficiency at 100% load. That way they're the most efficient throughout the power band, and that's what makes pretty much good kinetic drive motors. And you can see it in the power band here. Since turbos make more power the more you rev, more efficiency the more you rev the motor, and superchargers make less efficiency, the supercharger is on the core, the turbos are on the exhaust. So the two formulas, if they had the exact same efficiency, what would happen would be as the supercharger dropped off, the turbos would kick in and make up for it, and you would have the exact same efficiency throughout the power band. And you can see that here in this motor. The turbos are never reach the efficiency of the supercharger, and that's why this motor starts off at 184 and it drops down to 176, drops down to 168, because the turbo creates more efficiency at the low end. The turbos are doing nothing, and then as the turbo falls off, as the supercharger falls off, the turbos are not ramping up to meet the efficiency of the turbo. So we start with a high efficiency motor, or relative, it doesn't even make my chart, but the efficiency starts the highest it's ever going to be and starts dropping off because the turbos are letting us down. They're not taking the slack for what the turbo is dropping off. Now in this motor, it gets more and more and more and more efficient. So at lower RPM, it's more efficient because the supercharger is creating a high efficiency, and the turbos are creating a low efficiency enough to overcome this motor. And as the supercharger starts to fall off in efficiency, the turbos just start getting more and more and more and more and more efficient. To the point where they're actually more efficient than the turbo, so the efficiency rating goes through the roof relative to this motor. So this is the primer for the power band and what motor does what. This motor tells me that the supercharger is doing all the work and the turbos are doing nearly nothing. This shows me that the supercharger is doing me good at low end, but the turbos surpass it at efficiency, and that's important moving forward, because if we could get turbos to surpass the efficiency, and then after we get past 30 exhaust, we can make motors that reach maximum efficiency at lower RPMs. We could start making, if you wanted to do it, make a motor that would be more efficient in the mid-range. And a good example of that would be this motor. Say we wanted to run this motor, we would tune it for, say our boat used 800 horsepower. We would tune it to make maximum, or in this particular case, let's say our boat uses 1700 horsepower continuously. The motor would be running at maximum efficiency, and then in combat we could get way more horsepower. We could go from 1500 horsepower all the way to 6400 horsepower. Sure, we'd fall off in efficiency, but combat doesn't last as long as you going back and forth getting ammo and fuel and just navigating the map. So if you wanted this motor to be kinetic drive, if you could keep it somewhere in the 1500 horsepower range all the time, and then just use it in combat for full power for when your shields would turn on, it would make this the most efficient kinetic drive using those parameters. So that's how we use series parallel exhaust systems, and how much exhaust is fed into the motor to make it reach different efficiency levels, and how we kind of tune motors for different applications. And it shows up in the power band. Now, most small motors, since we can't get I'm gonna have to put up railing there. I keep falling into build. Most small motors, since they reach since the turbos give us maximum efficiency, even on this little on a single cylinder, 4 turbos could get us more efficiency than a supercharger. The more exhaust we could feed into this, the even more efficiency, up to 393%. It would be more than 10 times more efficient than that supercharger. And if we didn't need kinetic drive to where we're going through the entire power band, or we blocked off that supercharger where we could share another piston with it, we can take the 4 exhausts from that piston and feed it back into the system and get it even more efficient. And so your motor would become even more efficient at higher powers. And that's why I always say running your motors at 100% is pretty much the best. But the point is that the more exhaust we feed into this system, the more efficient it becomes. Well, with only one cylinder, we can only get 4 exhausts. So we could only get the efficiency, I think it was 54%, is about the max we could get out the turbo. So what that's telling me is when I run this motor, it's never, the more I can rev it, the more exhaust I could get, the more efficient it will be. So since I can only get 4 exhausts to it, it's going to reach maximum power at maximum RPM. If I could get 8 exhausts in there, it would get even more efficient. But since I only got a single cylinder, I can't get 8 exhausts. So you have to start moving into multiple cylinders to get more exhaust, because that's what happens here, that the efficiency doesn't really improve much over that because it's still a single cylinder. The only thing we did here, the problem that we did here is we put 3 carbs on it to get more power, but in doing so, we only have 2 exhausts. So this motor can't ever be efficient as this motor because it only has 2 exhausts. There's no way to really push the exhaust count up. But as you start getting into 2 cylinders, this one is collecting 1, 2, 3, 4? 4 from that cylinder. It looks like 4 from that cylinder. So it's sharing a carb and it's picking up more exhaust. So this motor technically should be more efficient. And it's making 200 horsepower, I think, using almost the same fuel. Yeah, it's making twice as much horsepower using the same fuel. And then when we go into the 3-cylinder, I could pick up even more exhaust. So it gets up, you could see where it's hard to make really efficient motors out of a single cylinder. The way you have to do it, like in this motor where I've only collected 3 exhausts, I've collected 3 exhausts, but what I've done is I've put 3 exhausts. I had to go into 10 turbos, and I guess what happens is at a 73% efficient range with 10 turbos, it becomes more efficient than 4 exhaust with only 4 turbos. So there is some kind of trading off there, and what I normally use is, I would say the minimum you would want would be 2 turbos per carburetor. 3 turbos gives you more efficiency with less exhaust, but then you lose more connections to your turbo to collect more, to your carburetor for sharing, and then you lose, you start losing. There's trade-offs to be made no matter what. So if you want an efficient motor, you're always going to want 2 turbos per carb. 3 can be better. 4 can be even better. 5 could even be, which is what makes this motor so efficient. It's 5 turbos on each carb, and then there's 2 carbs on a single cylinder. So that's how I was able to get this motor up into the real high C rating, but it's not very space efficient, and you can't do a lot with two turbos. But since it's only collecting 3 exhaust, the efficiency really can't get too much higher, and it can't get to maximum efficiency with 3 exhausts. So no matter what, this motor is going to top out at 100%. And if I could rev it faster or get more exhaust to it, I could make it more efficient. This thing would probably be a 0 fuel motor if I could get 20 exhaust to it. It would be no problem for that. But the point is that small motors, you can't get enough exhaust to the turbos to reach maximum efficiency. And when you want to get to about 30 exhaust, which is what the design goal for this motor was, to collect 15 exhausts from 15 cylinders on this side, 15 exhausts from 15 cylinders on this side, and then feed it into my turbo chain and get maximum efficiency at 100%. And I thought that would be the holy grail of efficiency. And then since this didn't break the binding box, I collected an extra exhaust here. And if we run the motor and we look at the turbo, it's 393% efficiency, but it's getting 31 exhaust gas. And what that 30 extra 1 exhaust gas does is, instead of being maximum efficiency at 100%, it makes it maximum efficiency at 97%. And I can show that real quick by let's go into build mode, and I'll get rid of this exhaust and just put a straight pipe in there. And now we'll get exactly 30, and if we run the motor, it's probably going to get maximum efficiency at 100%. At 1228. No, it's still doing it. I don't know why it's doing that. Okay, but it uses, you see, it uses 1.2 fuel at, whereas before with 31 exhaust it was using, it was reaching maximum efficiency at a lower point. So what it did by removing that exhaust, it has become less efficient in the top end. Notice that we're now using 1.2 fuel all the way down, whereas before it was using 1.1 fuel at 97 to 99%, and it would only use 1.2 fuel in the last percentile. So getting more exhaust to your cylinders, to your turbos, does make it more efficiency in the mid-range. And we'll see that in future motors, that you could get the mid-range more efficient than the top end by overfeeding exhaust to your turbos, but it does affect the power band. So trying to get, like, by adding that extra exhaust, all it did was drop off 0.1 fuel across the board. So that's pretty good. That's a pretty good little gain, and it didn't break the binding box, and that's why I did it on these motors. Okay, but it shows that when you start getting into bigger motors where you can actually get 30 exhaust, you start seeing, not all, but a lot of, I'd say almost 80% of the motors on my platform reach maximum power at 100% load, meaning that there is more efficiency left on the table. And this is a good example where it reaches maximum efficiency at 97%, and then kind of falls off because it uses not this one, it uses 1.1 fuel at 97%, and then when you go to 100 it uses 1.2 fuel. So it's fallen off of the efficiency curve, and this motor I learned a lot from because of that. And there's very few motors on here. I think this one does it, gets maximum efficiency at 42%, and this one gets maximum efficiency at 24%, and I think this one does it at 40-something%, at 47%. So that makes motors that are more suited for kinetic drive, and motors that reach maximum RPM at 100% are better suited for generators running at 100%. So that's what the importance of series and parallel exhaust is. We're parallel collecting, even on what they call an inline configuration. We're collecting the exhaust parallel, and then we're sending it series through the carburetors. And then a parallel collection with parallel turbos, we pretty much don't want to do. This is the only motor that's on the platform like that for demo purposes. And that's the way to go because that's where the maximum efficiency is. And then we could tune maximum efficiency. If we can get 30 exhausts collected, we could tune the motor for maximum efficiency at 100%. If we get more than 30 exhausts, we could tune the motor for maximum efficiency at different power ranges, which is pretty important, because if you had, say, the little 3T heater motor, if I could get more exhaust on it, I could maybe feed half of the exhaust through half of the motor and half of the exhaust through the other half of the motor, and make two series parallel configurations on the same motor and tune it to run differently, even though it uses the same exact blocks. But since it's a little small motor that can only get, I think it only gets about 12 exhausts, and it's real easy to check. You just run the motor and go look at your turbo. It's getting 14 exhausts. So this motor, it just tell you that this motor is going to top out, be 100% efficient at 100% load. And then, but when you start getting into about 8, I would say about 8 cylinders and up, is where you start getting, so you can start collecting so much exhaust that you could start tuning the motor different for different applications, and that's really important. And it's pretty much the end of the scope of this video, but it shows that motors can be tuned, I would say 8 cylinders and above can be tuned for different applications, and that turbos surpass the efficiency of superchargers, and that superchargers are dumb because they get maximum efficiency at low powers where you're not making any power. So yeah, okay, you can get, let's say you could get a 1,000% efficiency, but you're making 1 horsepower. So 1,000% efficiency, would make the motor use no fuel, but you're not using any fuel anyway because you're not making any power. So, and then when you start making power, the supercharger starts to fail, and you need turbos to take up the slack. So that's why I say superchargers are dumb, and that turbos are the most interesting thing. And there is some correlation between the number of exhaust you feed turbos, and if you don't have a lot of exhaust, you want to make up the difference to the fact that you don't have a lot of exhaust. You got to use a lot of turbos to get the motor efficient. But then it becomes space inefficient, and you could get a more powerful motor in that range. So a good balance is usually about 2 turbos per carburetor, and some instances, in some spaces, 3 turbos per carburetor is better, but most of the best motors have at least 2 turbochargers per carburetor, and they have a supercharger if it fits, because even at 100% load you get like a little 3% extra. So even if you're getting maximum efficiency out of your turbo, you would cap out, and there's no more efficiency left to be had in the turbo. By putting that supercharger in there, even at 100%, you get an extra 3% efficiency. So if it fits, put it in. If it doesn't, don't worry about it. It's only like a little 3% efficiency. 3% efficiency out of 393. It's less than a 1% difference. I think it's like a 0.1% difference. But anyway, that shows that turbos are probably the better way to go. They're more tunable. They add, if you don't use turbos, you lose out on a secondary formula that could be manipulated a lot more than what you could if you just used the core parts, which is the block, the cylinder, the supercharger, and the carburetor. So that's why turbos in a parallel collection serial configuration is the best, because it's the most efficient. It can't quite beat out in space constraints, because the density of an injector motor is way more dense, but for its density it gives back a good bit of fuel efficiency that a injector can't even touch. And so that's why I build efficient motors and that are a little bit bigger than what most people could create for the same power, but they're drinking a crap ton more fuel, sometimes in the 10 and 20 times magnitude more fuel. And then the space I use up, I save in gas tanks. It's easier to armor, and I don't spend my entire campaign going to look for the deep guard space and going, oh man, I'm at half fuel capacity. I have to turn around and go back and get fuel. I waste less time doing that. Some of my boats, I start a campaign and I'm 6 hours in and I'm still like at about, a half of my fuel, and I get through a major battle where some of my tanks get exploded and I'm like, wow, I'm down to like 10% fuel. I got to go back and get fuel. Well, most people, if you got a really gas guzzling engine, you might not even make it back to your fortress to get fuel. So you have to steal fuel, transfer some fuel off of a nearby ship so you could go back, and that just keeps more firepower in my fleet in the game, and I spend less time managing fuel refueling. So hope that guys shows you guys. I hope you really need to understand the series versus parallel turbochargers and why it's important, because of the two formulas, and that lets us tune motors and affect their power bands for different use cases. And it's really, really important moving forward, and we need to understand it. And I see you guys in the next video.